So without further ado, I'd like to introduce Dr. Phil Klotzbach. Phil has been at Colorado State University. He's really doing a terrific job with seasonal forecasting with hurricanes, and has done a lot of research and continues to do a lot of research into what's driving that seasonal variability. So we want to introduce Phil sort of through a video that was produced on the 2017 hurricane season because it was so dangerous and deadly. Take a look at this, and then we'll bring Phil to you for his presentation. Take a look.
The 2017 hurricane season was epic.
Tragic. Historic.
Hurricane Harvey started taking shape August 17th, rapidly intensifying just days later. But no one could imagine what was coming next.
It was a scene like this that was unending. It went all night and throughout the day. And the rainfall rates, they were up over 6 inches per hour. It felt like it was never going to end.
All the computer models that we looked at, all of our worst nightmares as meteorologists, you see those images and you're like, well, sadly, this forecast verified.
The rain kept coming. Before long, parts of southeastern Texas were covered in more than 5 feet of water.
It's terrifying to see these waters rising and not knowing what to do.
This is a street, not a river. Seeing just family after family after family doing whatever they can to try to get to higher ground.
More than 120,000 people were rescued from floodwater. 203,000 homes damaged or destroyed.
This really gives you a feel for how powerful water can be. And to watch this entire roadway collapse, just astounding.
According to the governor of Texas, Harvey could end up costing around $170 billion. But this hurricane season was far from over.
Irma spent 3 days as a Cat 5, setting a new record for that in the Atlantic. It also made 7 different landfalls, each as a major hurricane. Irma was a beast.
Hurricane Irma made one of its landfalls in Cudjoe Key, Florida, with winds of 130 miles per hour. It made another on the state's west coast.
This is an eye wall.
Here's Bettis in Naples. He's getting hammered in the eye wall.
Being in that eye wall, it was easily the strongest hurricane winds I'd ever experienced.
We're in Fort Myers, so we know this is coming toward us.
Irma ran up Florida, hitting other states, including Georgia.
Ooh.
You know, if this car was a little bit faster, that would have come down right on the driver, and wow. And again, this is in Georgia. The winds weren't as strong, but they were strong enough.
More than 70 people in Florida were killed during Hurricane Irma, with the total damages estimated at $25 to $65 billion.
It's heartbreaking, the amount of destruction. I don't think anybody was prepared.
Right behind Irma, another monster, Maria.
We just couldn't get a break.
Hurricane Maria struck Puerto Rico as a Category 4 storm, 155-mile-per-hour winds at Yabucoa, while heavy rain over 2 feet fell in the mountains, triggering landslides.
I mean, it is just a river of mud.
You literally have this almost zero visibility in blinding rain. You can't see much at all. Wind gets in, it's got to find a way out.
The aftermath becoming one of the worst humanitarian crises in modern times.
People there didn't have much, and they're still offering it to us. We're like, no. But that's their spirit.
Seeing the aftermath of these storms on video is jaw-dropping.
When you look at Harvey, when you look at Irma, when you look at Maria, we've seen the worst hurricane season possible.
Well, good morning, everyone. Thanks for all of you for sticking around through the end of the summit this morning. And I'm going to kind of dovetail on a lot of the stuff that Jim was talking about, focusing on hurricanes, which obviously became a very hot topic of conversation in 2017. You know, being in Colorado in the backwater. Dr. Gray, my now deceased predecessor, used to always talk about, people would say, why do you do the seasonal hurricane forecast from Colorado State? And he would say, because the storm surge can't get you at 5,000 feet. So, but with that being said, I do want to start by acknowledging Dr. Gray, who was my mentor. He was my PhD supervisor and just an all-around great person. And he did a tremendous amount of research, not just with the seasonal hurricane prediction, which is what he's best known for amongst the general public. He did a lot of research just in basic tropical convection, as well as tropical cyclone structure, intensity change. He's the first one who kind of documented globally why storms form where they do, and he came up with some of the large-scale physical constraints, why hurricanes form where they do and why they don't form in other areas, say like off the west coast of South America. And so myself and a few of his other PhD students, we published a paper, was in the November issue of the Bulletin of the AMS, on Dr. Gray, highlighting a lot of his contributions.
Dr. Gray attended this conference several times, and he was an incredibly nice man.
Yes, he was a very, very nice guy. He was just an all-around great guy, and certainly he certainly fit the nutty professor description too. I have plenty of Bill Gray stories if we want to go down that rabbit hole. So today we're going to cover a whole pile of topics. We'll start with the basic introduction about how seasonal hurricane predictions, how we do our seasonal hurricane forecasts. We'll then talk about multi-decadal variability in the Atlantic Basin, a little bit of talking about the global ocean circulation, which Jim already talked about a little bit, kind of evidence for some of these, when we have these kind of periods where the global temperature does kind of level off, how you see people talking about it ending up in the ocean, and we'll talk more about that. Tropical cyclones and climate change. It was kind of a quiet topic for about a decade. This year it came right back to the forefront. So we'll talk about some of my own research on this topic. Talk about 2017. Weather Channel just did a nice thing, so I probably can pretty much skip that now. But no, we'll spend some more time talking about what happened, why the early seasonal forecasts weren't anticipating a lot of storms, and what ended up happening. A little bit about 2018. We're still a little too early. This is January. The hurricane season starts June 1st, but it really doesn't start till August. So it's just a long way to go. So the climate models this far out aren't very good, predicting weather 6-8 months out. And I'll talk about a couple new products that I've been working on the last few years. One of them is a seasonal forecast website compilation that I put together in partnership with the group actually from Barcelona and Spain. So we have all the seasonal forecasts that are publicly released by universities, government entities, and private sector companies, so you can kind of see the ensemble of all the different forecasts. And also a real-time global tropical cyclone statistics website, which suddenly became very popular last year as Atlantic Basin accumulated cyclone energy went up asymptotically for a few weeks. So yes, Dr. Gray unfortunately passed away in 2016. I do actually have a new co-author on the forecast, Michael Bell. I actually know him from back when he and I were both getting our masters and PhDs together. And he joined CSU's faculty 2016, so 2 years ago now. And so he's a great guy, and hopefully one of these years you'll get a chance to meet him as well. Seasonal forecast is more than just these dudes waking up in the morning looking to see if we can see our shadow. I don't like to knock my meteorological namesake Punxsutawney Phil too much. Groundhog Day is coming up. But we do have long-term skill. We started putting out these forecasts in 1984, and the fact that we're still putting them out today and people still pay attention to them indicates that these forecasts have some skill. We're not throwing darts at a board. So while we would agree with the great philosopher Yogi Berra that it certainly is tough to make predictions, especially about the future, and all of you in the weather prediction business sure would agree with that statement, we also find, like Yogi would say, that you can see a lot by looking. We use statistical methodology and historical data to come up with our seasonal hurricane forecasts. So we have, going back in time, we know which years in the past were active hurricane seasons. We all know 2005 was a phenomenally active hurricane season. We also know a year like 2013 and the Atlantic was incredibly quiet. So we know these years were active and inactive. And we also know now we have globally gridded data where we can go back and say, okay, what were the weather patterns like during those seasons and prior to those seasons? What were the ocean temperatures like? What were the wind patterns like? What were the pressure patterns like? And we can go back in time with this data and come up with statistical modeling. Basically, how well would these various predictors have worked forecasting past years? And then we apply them to the future. Now, the challenge is as you go back further in time, the data gets sketchier. The hurricane data gets sketchier, and the global weather data gets sketchier, especially prior to the satellite era in the mid-60s, and then especially prior to, say, the late 1950s when they weren't launching weather balloons as often. You don't have good upper-level data. So as you go back in time, your weather data gets sketchier. But it's gotten a lot easier since when Dr. Gray started coming up with these forecasts in the mid-1980s. There were none of these globally gridded products. So Dr. Gray was literally calling up people and saying, can you send me station data for specific weather stations? So it's kind of a testament to his creativity because he kind of already knew what he was looking for, whereas now anybody can go online and take a time series and correlate it with any climate index that they want and come up with all sorts of things. But the key is understanding physically why these parameters would be related. So just to give you an idea, here's a composite showing the 10 most active hurricane seasons since 1950 minus the 10 least active. And surprise, surprise, yellows and greens are warmer, blues and purples are colder. So hey, more active hurricane seasons, the Atlantic is warmer. Makes a lot of sense. Hurricanes live off of warm ocean water. But it's not just the warm ocean water by itself. When you have that warm ocean water, it tends to be associated with lower pressure in the tropics, weaker winds, more low-level spin. So when these systems come off Africa, they move into a more conducive environment. Last year, the Atlantic SSTs were in the main development region were about the 3rd warmest on record using the satellite era data. So it was the atmosphere was certainly, or the ocean was certainly primed for an active season. But if the Pacific was warm, if we had had El Nino last year, it wouldn't really have mattered. El Nino tends to dominate over any other signal. But last year, while the models early on were forecasting, hey, El Nino's coming, those forecasts were lousy. We ended up with a weak, cool neutral to borderline weak La Nina conditions. And overall, we saw a very active Atlantic hurricane season. So we have these kind of precursor signals that we can document. One of the big ones, again, is the El Nino phenomenon in the tropical Pacific. It drives weather globally, and its impacts are for the Pacific Ocean. When you have El Nino, you tend to have a lot more activity in the eastern Pacific, especially towards the central Pacific, towards Hawaii. In the western Pacific, the storm tracks shift further east, so you get these long-lived typhoons that tend to become stronger. So overall, globally, your best bang for your buck if you want an active global season is the West Pacific. You want to have an El Nino. That gives you your most global storm activity. Like last year globally was a down year. Even with the Atlantic going gangbusters, the Atlantic just can't generate as much as the Pacific. The Pacific's a lot bigger ocean, a lot larger area of really hot water to deal with. But for the Atlantic, El Nino is our friend. Typically, when you have in the Atlantic, you have low-level trade winds. So the low-level winds are out of the east, and upper-level winds blow out of the west. So you have a shearing in the vertical, which, while conducive for tornado formation, is not conducive for hurricane formation. Hurricanes generally want to be pretty much upright. So if you have a shear in the vertical, it tilts the hurricane circulation. You can't get the deep pressure fall that you need. You get more entrainment of dry air, more mixing of dry air into these deep thunderstorm complexes that are trying to develop. So consequently, El Nino is generally our friend. It reduces basin-wide storm activity and also tends to knock down storm activity hitting the US coast. The signal, though, is much stronger along the East Coast than it is along the Gulf Coast. People always say, okay, it's a quiet season. What does that mean for the Gulf? Really not that much. And that's because Gulf of Mexico storms can form in a whole... So typically storms hitting the East Coast most of them form from waves moving off the coast of Africa that hit the East Coast. Whereas Gulf of Mexico storms can form from those, but they also form in situ in the Gulf of Mexico or, say, in the Bay of Campeche, Western Caribbean. So the signals are weaker for the Gulf of Mexico than they are for the East Coast. So now I want to talk about this multi-decadal variability that occurs in the Atlantic Basin. The Atlantic, going back in time, has had periods of a lot of storms and then similar length periods with many fewer. And for example, I'm sorry, this doesn't come out looking that great. But basically, what you have since 1995 is, in general, more active Atlantic hurricane seasons. And it's strongest for the Category 3 to 5 hurricanes. These are the major hurricanes, winds of 111 miles an hour or greater on the Saffir-Simpson wind scale. So while these storms make up only about a quarter of all the storms in an average year, they do about 80 to 85% of the normalized damage on the long haul. Obviously, the three kind of the biggest stories in town from this year, Harvey, Irma, and Maria, were all these major hurricanes. But if you go back to 1970 to 94, we averaged about 8 major hurricane days per year since 95. Back to 70 to 94, we were down at only about 2.5. You go back to 26 to 69, we were much more active, and then much quieter from 1900 to 25. Should point out these first two periods may be underestimated a bit, especially prior to the aircraft reconnaissance, especially prior to around 1950. We just didn't know if storms were in the eastern Atlantic. Typically, your strongest hurricanes are more in the western Atlantic, so you probably didn't miss a lot of the major hurricanes, but those numbers may be underestimated a bit. So what drives this kind of multi-decadal variability? Well, we're going to talk now about the Atlantic thermohaline circulation. And this is really Dr. Gray's baby. He talked about this all the time. If you saw that great scientific film, The Day After Tomorrow, which came out in, 2004. So it's been a long time. But, you know, the week after that movie came out, I had several reporters calling and asking about the thermohaline circulation. And normally, nobody ever asked about that stuff. So it did put it into the popular lexicon. I did convince Dr. Gray to go see that movie, which was very entertaining. He tried to tell me the last movie he had seen in the theater prior to that was Gone with the Wind. I think he was joking. But all that to be said, the thermohaline circulation is so named because it has two primary components, thermo for temperature and haline for salinity. And if you look at this graph, you can see yellows or greens and blues are lower salinity, reds and yellows are higher salinity. And you can see nicely the subtropical high regions where your evaporation exceeds your precipitation, you have higher salt. But if you look, the Atlantic got bright reds, the Pacific, they're not as bright. And that's because you don't get the mixing between the Atlantic and the Pacific in the equatorial region since the Isthmus of Panama filled in, like you do between the Pacific and the Indian Oceans. Only mixing you get down is by the southern tip of South America. So consequently, you have higher salt content in the Atlantic Ocean. Then what happens is you have this warm, salty water in ocean currents such as the Gulf Stream, and then it moves northward and northeastward, encounters colder air, and the water begins to cool. And at temperatures near freezing, the primary driver of density of the ocean water is the salt. So you have this cold, salty water that's dense, and it can sink to deep levels in the ocean in a process that's known as deep water formation. When the Atlantic is a little bit saltier, you have more warm water moving up into the far North Atlantic, less of a return flow because you have water sinking, more water sinking, you have less water coming down along the west coast of Africa, which is why if you look at this multi-decadal signal, it's often called the Atlantic multi-decadal oscillation, or AMO. It's kind of this horseshoe-shaped pattern where you get warm in the North Atlantic, warm along the west coast of Africa, and then warm into the tropical Atlantic, which is how it impacts the hurricanes. Alternatively, when the circulation is weaker, you get less water sinking in the far North Atlantic, consequently you get more of a return flow along the west coast of Africa, which is bringing colder water down out of the north, cooling the tropical Atlantic and generally suppressing hurricane activity. Now, this is a climate kind of argument, so you're talking about 20, 30-year periods, and you're doing all these kind of binning averaging. It's not to say that you can't have very active seasons in a quote-unquote inactive era, or complete duds of seasons in an active era. Typically, those are El Nino driven for quiet seasons and active eras, but there can be other factors that come into play as well. For example, 2013, we think we were generally still in the active era, but it was a very quiet season even with no El Nino, and that's because we had a lot of extratropical interactions. We had fronts coming into the tropics, which you typically don't see during August, September, so we had a lot of shear coming in associated with those. But on the long-term time scale, this is the way we believe is the primary driver of this multi-decadal cycle, not focusing on the climate change, the longer-term time scales. One of the things I wanted to point out, though, is the question is often asked, well, why does it kind of oscillate back and forth? And we think it's probably more of a discharge-recharge mechanism, whereby when the circulation is going strongly, you have more water sinking in the far North Atlantic than the salt is being built up in the subtropics. Likewise, when the circulation is weak, you're building up more salinity in the subtropics, and it gets advected further north, and it begins to sink at a higher level. This Atlantic thermohaline circulation is part of a global scale circulation known as this meridional overturning circulation. So water going down in the North Atlantic has to come up someplace else, and it tends to come up in the Pacific and the Indian Oceans. And when you have an enhanced or a stronger overturning circulation of the ocean, basically what you end up with is when the Atlantic is warm, the rest of the globe actually tends to be a little bit cooler. So in this recent active era that we have been in from the late 90s to say 2012, 2013, the globe had its period of not much warming. And we saw in the earlier slide that a lot of that went into the oceans, and that's because you had this greater enhanced overturning. But consequently, the last few years, the North Atlantic has cooled a little bit, and the rest of the globe has suddenly gotten warmer. And we saw from his figure a few minutes ago, that big spike the last few years, the overturning has likely slowed down. And so consequently, you have the Atlantic kind of going opposite of the rest of the globe. So it's not just the ocean temperatures that matter in the Atlantic. When you alter the ocean temperatures and the currents, you then alter your pressure patterns, your wind patterns, which alters your shears. So it's all this stuff part and parcel that go together to come up with an active or an inactive Atlantic hurricane season. One thing I like to point out, though, is when people say, well, what about with your seasonal forecast? What predictors do you use? from a statistical modeling perspective, whether I use the water temperatures in the tropical Atlantic, the shear, the pressure, once you put one of those into the model and you say you want to add one of the other, if you say you put shear into the model, then you add sea surface temperatures, your model skill doesn't improve hardly at all, and that's because they're so tightly correlated. Once you've put in that one predictor, you've got most of the variance that you can explain from stuff going on in the tropical Atlantic. You have to look further afield for other predictors to improve the skill of the model. So you have this multi-decadal signal going back in time, and we see it high since 95, then low 70 to 94, high from the 20s to the late 60s, low from 1900 to 25, and generally warmer during the late 19th century. Now on a longer term time scale, if you look at global temperature since 1900 or so, and you look at linear trends in global temperature, basically it's gone up everywhere, except in the far North Atlantic. There's this one little cold blob, the one area where it's gone down a little bit, and we think perhaps this is a longer term, potentially weakening of the overall overturning circulation of the ocean. So there's a variety of indices used to monitor this multi-decadal cycle in real time. There's an official index from NOAA, which is basically the surface temperatures in the North Atlantic, north of the equator. Whereas I have an index that I've developed with Dr. Gray about 10 years ago where we look just at the far North Atlantic water temperatures. And the reason that I want to do that is because that's where the deep water formation actually occurs. If you look at the NOAA's AMO index right now, it's pretty strongly positive, and that's because right now off the east coast of the US, it's stinking hot. We've had a real, well actually probably not right in this minute because we had several pretty strong storms going, I'm sure caused to take out a lot of heat out of the ocean. But in general, last few years it's been very warm off the east coast of the US. So you add that sea surface temperatures into the mix, you kind of muddle the signal in my view a little bit. But using this index, you can see high in the late 19th century, then low, then high, then low, then high. But overall, you can see certain years you do differentiate from the overall long-term signal. And that's because, again, there's a lot of there's multi-decadal variability, but there's obviously variability in the Atlantic and globally on much shorter timescales than that. But dialing in since 2014, in general, we've actually been in the multi-decadal cycle in the far North Atlantic. If you look at the far North Atlantic, it was generally fairly cold up there. And it's warmed up quite a bit recently. Right now, if you look at the far North Atlantic, it's actually warmer than normal. The Atlantic right now is hot. So if we basically took these anomalies that we have today in the Atlantic, combined with the weak La Nina, and said, we're going to start hurricane season today with those anomalies, then I would expect a super active Atlantic hurricane season with those anomalies combined with the La Nina. But obviously, a lot can change between January 18th and June 1st, and especially the hurricane season really doesn't ramp up until middle of August. And that's something I like to emphasize. Everyone does all their hurricane preparedness stuff June 1st, and then usually nothing happens for 2 months. And everyone says, oh, it's a dud. And you got to emphasize that that's typical. Hurricane season does start June 1st, but really, typically not much happens till middle of August. Dr. Gray used to ring a bell every August 20th and say, that's when the hurricane season really gets going. And 2017 was a classic case in point. We had a whole pile of weak pieces of junk early, but ACE was low, everything was pretty low. And around August 20th, if he was still alive, he would have rung the bell, and then that was about the time Harvey ramped up, and then it was bombs away for several weeks. So now I want to talk about tropical cyclones and climate change. Obviously, this is a hot topic, so to speak, especially after what we saw in 2017. This is a very challenging topic to deal with because what we have the best observations for isn't, so ideally what would be great is say, let's say we have 100 years of great global tropical cyclone data. We know the intensities of all these storms. We can just plot all this and we can see our storms getting worse. But the challenge is that if you look at what the climate models say for hurricanes, they generally say probably slightly fewer and slightly more intense, on the order of 5 to 10% stronger. So when you're looking for a signal of 5 to 10% in a time series where you really only have good data going back about 30 years, and you don't even measure these storms to within less than 5 miles. 5 miles an hour is what we measure them to. And other than the Atlantic, all we use is satellite data to estimate these storms' intensities, which have larger error bars in them. It's hard to detect signals in the observational record, which is what I primarily try to do with my various things. But obviously, if you look at damage from storms, the storm damage has certainly gotten worse. We have a paper that's that's currently in revision for the Bulletin and the AMS, looking at tropical cyclone damage. And we actually submitted this paper 2 weeks before Harvey came out. And we actually even had a focus in that paper on Harris County. But that was before Harvey came out. So we did point that out in the conclusion of the revised version that we sent in. But you can certainly see storms are doing a lot more damage than they used to. This is normalized for inflation. But obviously, there's a lot more causing storms to be more damaging than the overall storm intensity. You have a lot more people. We have a lot more stuff than our parents and grandparents did. So we're going to focus here just briefly on a couple of statistics. So we're going to focus on the Gulf Coast and the Atlantic because that's where the hurricanes hit. So if you look at the population by region, the Atlantic coast, so pretty much the east coast of the U.S., has doubled since about 1940. And the Gulf Coast has gone up by about a factor of 4. So we have a lot more people in harm's way than we used to. Likewise, if you look at the square footage of the average single-family home, it's gone from about 1,600 square feet to 2,800 square feet on average. So it's really, we have a lot more room for our stuff. Yes, exactly. And if you look, we didn't dial down in individual counties, but if you look at the homes that are being built along the coast, as opposed to being these nice, quaint little cottages that are like 800,000 square feet, they're now 3,000, 4,000 square foot monstrous structures, such that when these storms get damaged, the insured bill is very, very high. There's been a variety of studies that have tried to say, okay, well, let's take the damage that we observed at the time and then normalize it to today's values by inflation, but also population and wealth. And obviously that gets, there's a lot of uncertainties with those kind of estimates. But in general, most of them show pretty much no significant trend since 1900, which is what you would expect. I'll show you later the slide of landfalling U.S. hurricanes. So if you go back to 1900, you can see there are these big spikes. You have 1900 with the Galveston hurricane. 26, though, really, really stands out. 1926 was the estimated largest year, if that year to recur would generate the most damage, and that was very primarily by one storm. The 1926 Great Miami Hurricane was a large in size Category 4 hurricane right into downtown Miami. And obviously 1926, Miami Beach, not a whole lot on Miami Beach. Obviously today, a whole lot more stuff on Miami Beach. So let alone the storm maybe being, so basically even if the storm came in at the exact same intensity, all else being equal, it would do roughly $200 billion in insured damage if that were to occur today. Put that on a background of enhanced sea level rise, as Jim showed earlier. Just even on like a sunny day in Miami, you're getting sea level, you're getting water into downtown Miami. So you have that as a background as well. But even if the storm itself isn't any stronger, this exact same storm today would do $200 billion in damage. So even just looking at the past give you some pretty scary stuff when it comes to hurricanes. What I wanted to show you, though, is a lot of people want to look at landfalls. Because obviously, you have a phenomenally active season, nothing hits, people could care less, other than me. Most people could really care less if there's no damage. But if you look at the Category 4s and 5s, so these are the strongest storms, these are the ones that say storms are going to get stronger in the future. And you look at it from 1922 to 69, we had 14 Cat 4s and 5s, including 5 in 6 years in South Florida. And if you go from 70 to 2017, even including Harvey and Irma, we've only had 5. So from just using the Saffir-Simpson wind scale Cat 4s and 5s, we've actually seen fewer of these nasty hurricanes hitting the U.S. than during the prior time. But obviously, the max intensity isn't always the maximum, because obviously you have a storm like Charlie, which was a Category 4, intense winds, but small in size, so it didn't drive a massive amount of storm surge. Obviously, a storm like Katrina, which was a very large storm, had a lot more surge associated with it. But these are the kind of the metrics that we have. Unfortunately, we don't have great size data going back very far. If you look at landfalling hurricanes since the late 19th century, 1878 is when the Signal Service Corps started taking pretty consistent measurements. The trend is down. It actually was significantly down until 2017. That pulled the trend line out of that significantly downward line. But anyway, continental U.S. landfalling hurricanes, there's no trend since the late 19th century. Landfalling major hurricanes as well, no significant trend. Obviously, you see 2005 jumping out. This is all just focused on the continental U.S. You can treat the Caribbean differently. I treat the Caribbean differently, especially because you have a lot of nuances when people are always saying, like, how many landfalls did Irma make? And if you have a storm like Maria, Maria didn't make landfall in the U.S. Virgin Islands, but it still took out several of them. So when you have a very small island, especially given the latitude, longitude resolution, you can have a storm that didn't make landfall, but it can still do a massive amount of damage. So you have to be it's very tricky when you start getting into landfall, especially with small islands. But for the continental U.S., it's a lot easier to handle. If you look at Atlantic hurricanes, going back to 1878 and just plot them, that's a significantly increasing trend. But, of course, our observational capability in 1878 wasn't that great. Basically, we had ships. And ships didn't really like penetrating hurricanes. And also, there was ship traffic lanes. So there were certain areas where the ships generally just didn't go. And so what a couple of NOAA scientists did was they said, well, let's adjust for these missed hurricanes. And when you do that, you get a non-significant trend. So, and that, again, makes sense. We wouldn't necessarily expect to see increasing trends in the number of overall hurricanes. Now, if you look at the category 4s and 5s, which are the ones that we say are most likely to increase, there is an increasing trend since about 1950. Prior to 1950, the strongest storms, they just really didn't have the ability to observe them. But even in the 50s and 60s, we weren't flying the constant aircraft reconnaissance like we did with Hurricane Irma. In the case of Hurricane Irma, it was a category, it maintained 185 mile an hour winds for 37 hours in operations. But that's because they were flying it constantly. Had all we had was satellite data, we would have estimated it to be somewhat weaker. If you look at the automated satellite techniques at the time, they had Irma weaker. And I kept looking at the satellite and saying, oh, it can't possibly be that strong. And the plane kept measuring those winds. So the satellite can't necessarily tell you everything that's going on in the storm. But this would be a little more consistent with what you would expect from in the long-term record. They're reanalyzing all the historical category 4s and 5s in the Atlantic, or reanalyzing all the hurricanes in the Atlantic. So we may find some, they will be adjusting these numbers. Right now they're in the early 1960s, so these numbers may switch a little bit. I wouldn't expect to see many changes once you get to about the mid-90s or so. I'm sorry, this graph really did not show up very well. But anyway, anyway, this is the maximum tropical cyclone intensity that any hurricane had from 1950 to 2017. So the strongest of the strong each year. And if you plot the maximum intensity, there's a slight increasing trend. This wouldn't pass a significance test just using simple linear trend. But there is a slight increasing trend over the period record. And this includes Irma, which was the strongest max winds of any storm in 2017. The strongest hurricane in the Atlantic in terms of max winds was Hurricane Allen back in 1980. And then we obviously want to look globally because the Atlantic isn't the only show in town. And the challenge with the globe is that all we have is satellite data. We flew planes in the West Pacific till 1987, and then we stopped. Dr. Gray was not happy about that, but they stopped doing aircraft reconnaissance, so all we have is satellite data. And prior to the mid-1980s, satellite estimation techniques for hurricanes were not used uniformly everywhere, and they were using different wind pressure conversions from the satellite, and it's basically a can of worms, to use what Dr. Gray would have called it. If you get to about 1990, where the data is, oh yeah, go ahead.
Phil, just a quick question.
Sure.
Matt Safino, Portland. Are there no other nations that fly hurricane reconnaissance, for instance, in the Western Pacific?
They are starting to fly limited missions. I believe Hong Kong is now flying some limited missions. Taiwan flies a few limited missions, but they're very, very limited. For example, Typhoon Haiyan, which Jim showed at the start of his talk, possibly the strongest typhoon that we've seen, at least probably since like 1970 or so. Not one plane flown into that storm, and that's just criminal to me. Like, just get any plane, just measure what's going on in there. You know, at least get a measure of the pressure. No. So I mean, they're trying to do it. I mean, my personal opinion is it would be fantastic to have global aircraft reconnaissance. Don't fly every little piece of junk, but fly the big storms, especially ones that are likely to impact land masses, because it's shown time and time again that when you fly these storms, you find out things about the storms that you can't necessarily tell from satellites. Satellites can give you a lot of valuable information, but it's good to get that ground truth data from the planes, because in a case like Irma, it was stronger than what the satellites would have said it was, and that's important to know for people on the ground having to deal with them. And also you can measure pressure falls and things, and sometimes the satellite presentation may lag what's actually going on in the storm itself. But what I was trying to say with this is that If you start back in 1970 and plot the category 4s and 5s, and there were a couple papers that came out in 05 saying that Cat 4s and 5s have doubled in their percentage, and if that's the case, and that's a huge issue over 35 years with half a degree Celsius of warming of the oceans on average. But since 1990 or so, we kind of got fairly uniform satellite measurements across the globe. That number has stabilized, and there's actually been some theoretical papers that have argued that the percentage of Cat 4s and 5s may somewhat stabilize at around 40-ish% because you need other factors besides warm ocean water to generate a Cat 4 and 5. And obviously with climate change, you don't just warm the ocean surface, you warm the upper troposphere even more. And so from an atmospheric stability argument, that takes some of the edge off of the ocean warming. Plus the big question in the future, especially for the Atlantic, is what's it going to do to El Nino? And if you have a more El Nino-like basic state, which perhaps is more the prevailing view at this point, it seems like it kind of goes back and forth, various papers that I've read on the topic. But if you have a more El Nino-like basic state, the Pacific may go gangbusters, and the Atlantic may actually end up with fewer storms, or it may even have fewer Cat 4s and 5s if the shear is really strong. And I think that's something we really don't know at this point. One of the indexes that I use a lot, and I tried to push ACE a ton this year given how fast the Atlantic was generating it, is this accumulated cyclone energy, which is the wind speed squared every 6 hours that you have a tropical cyclone. And you add these together. And so basically what it does is it approximates the kinetic energy generated by the storm. Since we don't have great size metrics going back very far, this is what we kind of need to use to kind of get these big swings going back in time. And if you look at global ACE, you can see that generally the spikes in global ACE occur around the times of big El Ninos. Again, mainly because the Pacific tends to go up in El Nino years. This year we had a weak La Nina, borderline weak La Nina. So while the Atlantic was super active, the East Pac was fairly quiet after an active, really early season, and the West Pac was, I think, the 5th lowest ACE since 1950. It was pretty dead in the West Pac. But now let's move on. And obviously, if you guys have questions on anything that I've talked about, feel free to ask, because I'll blabber on about hurricanes till dinner if you want. But we can talk about 2017, which was kind of a non-event. No, obviously it was a phenomenally active season. This is a table basically just showing we had 17 storms. The average is about 12. 10 hurricanes. The average is about 6 to 7. But we had 6 major Cat 3, 4, 5s. Then the average is about 2. We had 19 and a quarter major hurricane days, which is a lot. The record for major hurricane days was set back in 1961 with 24 and a half. So this year was super active. It's on par with about what we saw in when you look at things like ACE, it's close to what we saw in 2005, maybe a little bit less, but a very, very active overall season. But obviously, what really set the season apart from a lot of recent active seasons that we've had, like 2010, was that the steering patterns were different, such that the storms, instead of staying out to sea and recurving, were all hitting land masses. And it seemed like the storms were wobbling as such to hit as many land masses as they could. And while obviously the season was devastating for Houston and for parts of South Florida, for the continental U.S., it was obviously incredibly devastating for the Eastern Caribbean. Irma and Maria were two, just basically what I called buzzsaws through that area. And when they said they hadn't seen storms this strong, if you look at hurricanes in the Atlantic, typically your strongest of your strongest storms are in the Western Caribbean, the Gulf of Mexico, where your waters climatologically are warmest. This year they were a little further east in the Eastern Caribbean. So those areas can get strong hurricanes, but not typically of the magnitude of storms, especially Irma, which to me, while the other storms were obviously devastating, Irma to me is really what kind of defined the 2017 season, because the sucker just wouldn't weaken. It was just this monstrously strong storm for a long time. When it comes to how the seasonal forecast from our group at CSU did, the early seasonal forecast, not great. Early on, we forecasted a slightly below normal season, and I'll show you why in a minute. June, we came up to near normal, a little bit above, and if you go July, August, the forecast numbers came up. And if you look at the seasonal forecast compilation website, in general, most of those groups were very similar, kind of starting off low and then going higher. And there were two reasons why. In April in the Atlantic, the tropical Atlantic was actually a little bit colder than normal. But we also had, the models were all calling for an El Nino. Here's the forecast from the European Center model, which is generally always kind of, everyone talks about, what does the ECMWF have to say? So this is an ensemble plume, so 50 members. And you have the ensemble from March. The red lines indicate, or the red lines are the forecast from the different ensemble members, and you can see in general, and blue dots is reality. So if you were issuing a forecast March 1st, and you say, well, I'm just going to eyeball the kind of the average, the midpoint, and maybe knock it down a little bit because the Euro tends to be a little warm, you'd say about +1 or so, which is a moderate El Nino. Typically, that's enough to really knock down the Atlantic hurricane season. But obviously, you can see it was outside virtually all of its ensemble members. This is its March forecast, is what we had available then. And this is its old forecast system. The new forecast system, which just came out, actually did even a little bit worse with 2017. So hopefully that was just a blip on the radar, and the new system will be better for future El Nino events. But El Nino has this phenomenon that's known as a springtime predictability barrier, which is fantastic because that's exactly when we need to do our seasonal forecasts. So basically, during the spring, your trade winds, which blow across the Atlantic but also the Pacific, climatologically are at their weakest. So very small perturbations in the winds can cause big changes in whether you get an El Nino or not. And so El Nino is basically a way that you discharge heat from the western Pacific, because over by Indonesia, the waters are generally very warm. So you have what's called the Western Pacific Warm Pool. The waters build up. It gets warmer and warmer. And eventually, you can't just get warmer and warmer forever. So the ocean basically will discharge that heat to the eastern Pacific and then send it northward and southward from there. But just because you build up the heat, sometimes it'll discharge a little bit of it, and then it'll kind of stabilize. And that's kind of what we saw last year. But overall, the seasonal forecasts from CSU have been reasonably good. This is our August forecast, which is our best seasonal forecast. While 2 months into the season, about 90 to 95% of all your major hurricane activity occurs after the 1st of August. Obviously, 2017 was a great case in point. A few pieces of junk in June and July, but really nothing to speak of till August. You can see in general the numbers are reasonably good. If you go back to June, the correlation is fairly similar, but you get about half the variability, which means there is unexplained variability in the system, and you're always going to have that with any forecast, because what we're trying to do is forecast a large-scale atmosphere-ocean environment, and typically a conducive atmosphere-ocean environment will generate a certain number of named storms and hurricanes. But it can change. Some years you can have more storms, fewer hurricanes. Like a year like 2005 had 28 named storms, but its ACE was only slightly higher than what we had this year with only 17. A storm like Irma, when you have a Category 5 for 3+ days, generates a whole lot of ACE in a very short amount of time. Not sure what, okay, so I'm not quite sure why slides aren't appearing. Yeah, I'm not sure. This should just be an animated GIF.
It's the ocean lag.
Yeah, it's the lag time. But anyway, I'm not quite sure what I can't remember what slide that was. So we'll just jump into basically the hurricane season. You look at it, September, this is the sea surface temperature analysis from NOAA closest to the peak of the season, which is climatologically around September 10th. The waters in the Atlantic were very warm. And we had a weak La Nina. So that's a recipe for a very active season. So it kind of fit what we would typically expect we would see for an active Atlantic hurricane season. You have more warm water fueling the storms, and you have less shear driving them on to reach those strong intensities. Because the warm ocean water will basically say, here's how strong theoretically your storm can get, and then the shear says, will I let you actually get there? Because you can have a super hot Gulf. For example, Gulf of Mexico every year is plenty warm. We've had years that we had like record heat in the Gulf and no storms there, and that's because we just didn't have disturbances tracking in there, and the shear was way too strong. So you need to have these combination of conditions to really ramp up the storms. So I did a 30-day average from late August to late September, which was Harvey, Irma, Maria, and Jose, which was really virtually all your ACE. And basically, if you look at the shear in the eastern Atlantic was near average, a little bit weaker than normal. But in the central Atlantic, the shear was very low. Now, climatologically in the Atlantic, the eastern Atlantic, the water temperatures are kind of cool, which is why you don't get major hurricanes usually at 30 degrees west. But as you move further west, the water's warm, but your shear also increases associated with an upper tropospheric trough. It typically increases your shear there. This year, you had the warmer waters in the eastern Atlantic, so these storms could ramp up as they got off of Africa. And then as they moved into the climatologically warmer water, which was even warmer, they also encountered an area of still relatively low shear. I like to look at the SHIPS model, which basically is a 5-day forecast, shears and moisture. And you looked at a storm like Irma, and to have 5 straight days of less than 10 knots of shear is virtually unheard of in the Atlantic, to have that low shear for that long. Combine that with 29 degrees Celsius SSTs, and you're going to get a beast of a storm. And all the models with Irma were pretty much calling for that from the get-go. It was a well-predicted storm, and following right on the heels of Harvey and all the horrible devastation that caused, the public, there was consternation from the get-go. I mean, it was even before the thing had moved off Africa, people were freaking out about it. And part of it was, too, the models all had it going west and south of due west, heading towards the Caribbean and then heading towards Florida. So it kept everybody up very long days, I'm sure, in this room. But really one of the things with 2017 was the steering was different. From 2006 to 2016, we had what was known as the major hurricane landfall drought. We had 11 years with no major hurricanes hitting the continental U.S. Now, major is only based on the max winds. Obviously, it does not include damage because Ike was devastating down in Galveston, off in Bolivar Peninsula, and then Sandy, which was kind of a storm, and it was just kind of its own. I mean, it was a superstorm, extratropically transitioning cyclone as it came ashore. But obviously with Sandy, its max winds weren't that strong. It was 70, 75 miles an hour when it hit, but it was monstrously large. So it had a huge surge associated with it. It came ashore, obviously, and it's basically impacted the most densely populated part of the U.S. coastline, so obviously did a huge amount of damage. But from intense storms, we hadn't had one in 11 years from a Cat 3 or higher. And that's because we typically had kind of an area of low pressure along the East Coast that helped to steer the storms away. Combined with some really good luck. Last year with Matthew, I mean, it was 50, 60 miles offshore. Obviously, that's just effectively luck. I mean, there's no 3-month-long average composite that's going to show you what happened with Matthew. But when people say, well, what caused the drought, it was basically, I think it was basically the storms tended to form a little further east. And typically storms forming further east, with the exception of Irma, tend to recurve. Where Irma came off, the odds of it hitting the U.S. climatologically were about 5%. But as one of my dynamics professors used to tell Dr. Gray, there's no climatology in the vorticity equation. So in the case of a storm like Irma, when you had a really strong ridge, just beat it south, and it kept going. So ACE by storm, Irma, 68 ACE. The only one higher in the satellite era was Ivan, which was another super long-lived, intense hurricane that was a buzzsaw going across. Maria and Jose. So Irma by itself, if Irma had been the only storm of 2017, it by itself generated enough ACE to meet NOAA's definition of an average season. That's how nuts it was. But see, a storm like Harvey, even though it was very strong, or it was reached Cat 4, hit Cat 4 and then went ashore, so it didn't generate that much ACE because it wasn't over the water for that long as a strong storm. Just to give you an idea, if you get rid of September, it was kind of a humdrum average season. September was the most active month globally on record. Even more, if you split the Pacific at the date line, it was even generating more ACE than any West Pacific month had ever generated. It was phenomenally active. We also set the record for the most ACE in one calendar day when we had 3 hurricanes going at once. It was a phenomenally active month during September. But the end of the season was actually, in my view, was surprisingly quiet. Given the fact we had a weak La Nina and we also had a warm Caribbean, typically that combination results in increased spin in the Caribbean, which tends to spin up you get that gyre in the Western Caribbean that usually spins up something. This year it spun up Nate and Philippe, but neither of them really were particularly strong. I mean, Nate was very strongly sheared and Philippe was very strongly sheared. My French namesake was not did not live up to its didn't really do very much in terms of its intensity. But I want to obviously talk a little. Oh yeah, go ahead.
Dale Eck from the Weather Channel. One thing I think we noticed after we went through that streak, and while all the models and we kept keeping our eye on the Caribbean, because you're right, that's a prime area. Just all of a sudden, shear developed at the mid and upper levels. That just we kept saying, well, it looks like something could form, but sure as heck ain't getting up here.
Yeah, and I didn't show the slide, but one of the things that we did see coming late, so this Madden-Julian oscillation, which is subseasonal variability, most of the season was fairly weak. So it wasn't a big. We don't think it was a big driver of the active September, but late September it really amplified, and in October it was basically in its mode that suppresses convection and increases shear in the Caribbean. And I think that really maybe saved the day from. I mean, if when I was compositing like September stuff, it looked like October should be gangbusters, and it just was. And we had Nate and Philippe, but nothing. Most of the ACE that came late was from Ophelia and stuff out in the middle of nowhere. Yeah.
Yeah, we've got another question on Facebook Live, and I wanted to try to get to it because our streaming may cut out.
Okay.
So Joanna Yen asked if you could explain why the 2005 season was so active.
Yeah, so 2005 and 2017 had a lot of similarities. Both had very warm Atlantics. The 2005, the Atlantic was even warmer than it was in 2017. Now, obviously, it depends on exactly where you're looking. That's just kind of drawing a box. There were a lot of differences between the 2 years, though, because 2005, it was like the season that just kind of went forever. It started around June and then just kept going into November, December. And they went through the Greek alphabet. And I mean, it was very. But the thing with 2005 is most of the storms formed fairly far west. So a storm like Katrina basically formed just east of, formed out in the western Atlantic. It wasn't an Irma or Maria. So they were similar in that they generated similar levels of ACE, but in terms of where the storms formed, they definitely were somewhat different. Both, however, had fairly similar steering in that they both had the steering such that kind of prevented recurvature, driving the storms further west so they could cause as much damage as possible.
With the similarity, yes, but can you say anything about why it was so active in 2005?
Yeah, I mean, 2005, again, the Atlantic was very warm, so it had lots of fuel from that perspective. I believe 2005 was the second warmest behind 2010. You had neutral ENSO conditions, so it was pretty near average, but the shear was pretty low. So that kind of, but again, the Eastern Atlantic wasn't super conducive in 2005, but it was very conducive further west, and that's what we saw in 2005. Obviously with Harvey, a lot of you know the storm better than I do, but obviously Harvey was a devastating storm, Cat 4 when it came ashore. It ended the U.S. landfall drought. However, if Harvey had just come ashore and done what a normal, well-behaved Texas hurricane does, it devastated Rockport, Port Aransas. I mean, the damage on there is horrible. But from a national perspective, it would have been kind of a blip in the radar because that area doesn't have a lot of population, so the damage it would have done was, from an insured perspective, was fairly low. However, the models did a great job forecasting that Harvey basically stalled. It couldn't go anywhere. And because of that, we saw epic rainfall, and it set the record for the most point rainfall, but I think more impressive was the swath of 30 plus, 40 plus, 50 plus inches of rain. Just a few stats on Harvey. Obviously, it was the first Cat 4 to make landfall in Texas since Carla in '61, which was to put Dan Rather on the board. First in the U.S. since Charley in '04. It ended the drought, but I think more what I wanted to get into was it was the longest lasting named storm on record after making landfall as a hurricane. So Harvey made landfall and it weakened below hurricane strength very quickly, but then it stayed as this weak named storm for a very long time. And so that was very problematic because obviously it dropped huge amounts of rain. And it did it so it broke the entire U.S. record, which is impressive given that the record was set in Hawaii, which had orographic impacts. Obviously, not a lot of orography in the Houston area. Yeah, oil rigs. Irma was a buzzsaw. I mean, you can pretty much generate any superlatives that you want for this storm. It was the strongest Atlantic storm on record outside of the Western Caribbean and Gulf. Tied for the longest lived Atlantic Cat 5. It had the longest sustained winds of 185 miles per hour of any storm globally on record. It's hard to compare with the Westpac because we didn't have constant aircraft, but it was certainly a very strong storm. Really, I think the thing that really stood out for me with Irma, though, was the damage that it caused in the Eastern Caribbean. It was the strongest storm on record to impact the Leeward Islands, where I kind of drew a 5x5 box around them, by 25 miles an hour, which is really, I mean, that's really strong. So when the guy came out and said we hadn't seen a storm this strong, based on the historical record, which for the Caribbean islands was probably decent until at least 1950 or so, they really hadn't. And it was very intense when it hit the Florida Keys. 929 millibar pressure, that's really low for a U.S. landfalling hurricane. 7th lowest, tied with the Lake Okeechobee hurricane, which was a devastating hurricane. Obviously with Irma, it was horrible. In the Caribbean, it was obviously devastating in Cuba, but the Florida was spared what could have been a worst case scenario. The Central Keys were pummeled. They were pummeled, but there was a lot of concern that it was going to track further west and go right up towards Tampa Bay. But right before it hit, it was obviously Cuba took some stuffing out of the storm, but then it was impacted by a lot of shear and a lot of dry air right as it was coming up along the west coast. And fortunately, it went in more up by Naples as opposed to up into Tampa Bay. So when you saw all the water getting blown out of Tampa Bay and places like that, when the winds on the backside of the storm had been cut off, they weren't as strong. So we didn't see the 8 to 10 feet of storm surge that some of the slosh model was showing for Fort Myers and Naples and Tampa Bay. So while the storm was obviously devastating, it wasn't the worst case scenario for Florida. Obviously, if it hadn't hit Cuba and had gone straight up the west coast of Florida as a Category 4, it could have been a whole lot worse. For Cujo Key, that area, though, it was pretty close to a worst case scenario. 929 millibars is a pretty nasty hurricane. And then obviously Maria, another incredibly devastating storm. Their strongest hurricane they'd seen since 1928. And obviously we're still seeing the damage. And still, it's going to just take years and years. And obviously, too, for Dominica. Dominica was absolutely pummeled. Obviously, 2 small islands, U.S. Virgin Islands, British Virgin Islands, and several of the small islands have just been devastated, too, with these storms. In the last couple minutes, I just briefly want to talk about 2018. So in December, we put out a kind of a scenario approach. We don't do full numbers because we just don't have skill in December. It took me about 10 years to convince Dr. Gray of that fact. But there is, at this point, if you had asked me 3 years ago, I would have said the multi-decadal signal, we maybe were in a weaker period. But I think at this point, given the far North Atlantic is still fairly warm, I think we have to say that we're probably still in this active period. So the big question to me hinges on, do we get El Nino next year? And in January, the model forecast for August, I mean, you may as well flip a coin. I think it's really just too early to say. Here's our current water temperature anomalies. If we transport these water anomalies to September 10th, then bombs away. It'd be a super active season. But obviously, a lot can change. We do have a pretty classic La Nina-like signal. You can see those cool instability waves in the tropical Pacific, and then you kind of see that nice horseshoe shape in the western Pacific. Here's the official probabilistic ENSO forecast. This is actually from December. They hadn't updated this by the time I had to send my final presentation in. But they're kind of splitting the difference. Their highest odds are neutral. The European Center Model forecast, again, we saw what it did last year. It's pretty much when you have this La Nina, typically you would expect it to go back to neutral in the spring, but the question is, where does it go from there? And I think there's just a lot of uncertainty. The upper ocean heat content, it discharged some with the kind of that failed attempt last year, so it's not a slam dunk we're going to get El Nino. The global models are kind of hinting that might be the case, but if I were to show you the same plot from last year, they would have been showing something very, very similar. So we need to be a little bit cautious about that. And I think I'll be doing a lot more statistical analysis of the El Nino, not just looking at the dynamical models in 2017. Yes?
Is there So comparing the two La Ninas, the one that we're coming, presumably coming out of right now, and the one that we came out of at this time last year, was the oceanic heat content in the Western Pacific higher last year than it is right now? So conceivably less to discharge.
Actually, I honestly don't know the answer to that question. That is a good question. I'll look it up and get back to you on that. But I think we did see it discharge some heat last summer because basically it got really hot off of Peru. And so there was a lot of thought, we're going to go into an El Nino pretty quickly, and then that just didn't pan out. But I can get back to you on what the current upper ocean heat content is compared with what it was last year in December and into January. This is the climate model from NOAA, the climate forecast system model for June to August, which is its latest forecast. It's still holding on to La Nina conditions, or cool neutral, and it has a fairly warm tropical Atlantic and a cold South Atlantic. And if that were the case, then that would generally lead to an active season. But again, these models don't have a lot of predictability at this long-term lead time. We'll put out our first forecast April the 5th, and that will be our first forecast with numbers. And we'll have more to say then. El Nino is still there's a lot of uncertainty in April, and our real-time April forecast skill is marginal. I mean, there's some there, but it's not a slam dunk. The forecast skill gets better, kind of like you would expect with a day-to-day weather forecast. Your 7-day forecast, if you verify that, maybe not great. 5-day forecast gets better. 3-day gets better. It even gets better. Unless you're forecasting for San Diego, then your 7-day forecast is perfect. So I do have a couple of new products just to finish off. If you like statistics, which you can tell I really do, I have a global website where I keep track of global statistics in real time. From the National Hurricane Center for the Atlantic and the East Pacific, and the Joint Typhoon Warning Center for the rest of the global basins. So you can kind of see, this is a screenshot from mid-December. You can see basically what each basin looks like compared with normal. Because I always want to know, okay, the Westpac's had 6 Cat 3 plus typhoons. Is that normal? Is that crazy high? Is that low? And so this gives you an idea to look at that. And when you click on one of these, it gives you information on each storm. So you can see kind of which storms generated the most ACE. And it's funny because I put this website out in 2016 and no one really used it. And last year suddenly it got a lot of use. I guess when you have a crazy active season, people start getting interested in that stuff. And I also have plots of ACE compared with climatology. So you can see 2017 cruising along, kind of humdrum through a late August, and then asymptotically then. Yes?
Yeah, a question about ACE. I mean, when you have a storm like Irma that really just is so much higher, that creates such ACE for the entire season, can you really look at ACE through a season and say that it was an active season if one storm is able to kind of skew that?
Yeah, I mean, I guess the question is, it kind of goes back to the philosophical question of what's the purpose of the hurricane in the general circulation. Because if it's truly to transport energy from the tropics to the poles, if that's one of its purposes, then you would expect that if that's what it's trying to do, one Irma could do what 4 Cat 1s could do. So from an ACE perspective, it's kind of trying to compare like 05 and 2017. If you look at named storms, there's no comparison. 05 was way higher. But if you look at ACE or like major hurricane days, they're a lot closer. And so if you look at ACE and correlate it with like the number of major hurricanes, it generally correlates pretty well. What I try to get people away from is just looking at the number of storms, because you can have a whole pile of pieces of junk. Like 2013, we had 14 storms. Okay, we had 15 in 2004, so they're pretty. But if the ACE was like 8 times more. So that's why we try to use ACE. I mean, there's really no, ideally what I'd love is a kind of a integrated kinetic energy, which takes in the size and the strength. But the problem with integrated kinetic energy is you don't have a very long period you can compare it with, because you don't have size data going back very far. Really, prior to scatterometers in like 04, globally it's pretty dodgy. The Atlantic can probably go back to the mid-80s. And then lastly, just the seasonal hurricane forecast website, seasonalhurricanepredictions.org. So we have all the different groups that are forecasting. But I will point out that we got a little bit of funding from XL Catlin, an insurance company, to put this together, because when I build a website, it looks like that. And when you have a professional web developer build it, it looks like that. So you can see what having a good web developer can do. So this will come online with 2018. Usually middle of March is when some groups start putting out their forecasts. I think AccuWeather usually puts one out middle of March. So I think we had 21 different groups give us forecasts last year. So it's pretty cool. And there's a little description of each forecast technique, how they're done. And then if you click, there's a link back to the forecasting agency so you can get more information. And it's only been live for 2 years, but probably in about 2 or 3 more years. Once we get several years, we'll start doing verifications to kind of see who's best. I don't like to verify for 2 years because that can be, someone throwing darts at a board can get it right 2 years in a row. And I always like to finish my talks with Arago's admonition, and especially in a group of forecasters. Never, no matter what may be the progress of science, will honest scientific men who have regard for their reputations venture to predict the weather. I would certainly agree that is still very true today. So with that, thanks, and I'll try to answer any more questions.
That's great. We do have time for a question if you want. We have lost the live stream, so we're not live streaming anymore because of the 4-hour limit. But we are recording this digitally and the videos, so if anybody asks you, hey, the live stream cut out, the videos of the entire presentation will be posted midweek next week on the Weather and Climate Summit website. So we can tell you that address. Yeah, Frank.
So we don't have to say our name? Still do. Frank Billingsley from Houston. Phil, you didn't talk anything about anomalous years that you show us when you put out your report. I always look at those years and see what happened to Houston in those years, or even the Gulf. And last year's years were all but one spot on.
Yeah.
I mean, Audrey in 1959, very active 1989 in Houston, but a lot of Gulf activity happened in those years, and then we had Harvey.
Yeah.
So.
Yeah, I mean, and it's tough because so when I look at those analogs, I'm looking at kind of the global. I haven't put analogs out for 2018 yet, which is why I didn't show them. But if you look at what I try to do with analogs is take several years in the past that had conditions most similar to what we currently have, and then kind of what we saw transition over the course of the season. And now if you say, Phil, pick out 5 analogs, I can give you my 5, but then if I ask a colleague of mine at the Hurricane Center who does the same kind of stuff, they may pick out, we probably have a couple that are the same, but they kind of very different analogs. And so I use both kind of the old school Bill Gray way, flipping through maps, but I also have like some automated techniques that have a few climate indices that I'll run, and I have like spatial correlation kind of programs that I've written to do it. And I kind of hybridize those, and I talk to some colleagues of mine that also do this stuff, and we kind of pick our analogs from that. I try to caution in terms of like looking at it for a specific city, because again, it's looking at kind of the large scale, and obviously whether a storm hits, you know, Texas versus Louisiana or Mississippi, that's obviously more nuanced than, you know, a 3-month average kind of weather. But I think there is a lot of benefit to looking at analogs, because you can do a lot from like looking at correlations, but it's helpful to kind of dial in and see which years looked similar, because sometimes you'll get 5 analogs and you'll have 2 years that were like stupid active, and then you get 1 year that was a complete dud. And that's good. It's good to know. And I don't put them in the forecast, but I also look for anti-analogs, so the 5 years that look least like this year. Because basically, if you get 5 years that look the most like this year, and they're all 2005 kind of years, and all your anti-analogs are these complete duds, then, you know, all hell's going to break loose. But if there's kind of a lot of scatter in there, that kind of indicates to you that there's just perhaps more uncertainty in the forecast. Oh, yeah.
Hi, Phil. Matt Safino from Portland. Any thoughts on indicators or controllers, be it ENSO, climate change, or other, on the East Pacific seasons?
Yeah, so the East Pac, ENSO is a very big driver, especially not right near the coast of Mexico, but further west. So if you remember 2014, 2015, very active East Pac seasons, a lot of storms tracking towards Hawaii, storms tracking over the international date line. That's a harbinger of an El Nino. Typically in the East Pac, when you have an El Nino, you have warmer water temperatures a bit, but really the primary driver there seems to actually be the moisture. You get more mid-level moisture, so it really amps up the intertropical convergence zone. And also, too, you kind of have this interesting inverse relationship between the Atlantic and the East Pac, such that you get a lot of East Pac storms form from easterly waves that come off of Africa and just don't develop in the Atlantic. So they cruise all the way across. And I guess you kind of figure if they're not forming in the Atlantic, they're still going to be moving on, potentially spinning up in the East Pacific. In terms of climate change, most of the stuff with climate change that I've seen shows perhaps an increased threat in the Central Pacific, which is a really marginal basin. Typically, you don't get a lot of stuff near Hawaii in that Central Pacific region. Usually, there's a very strong trough that tends to dig down in and bring a lot of shear down in that region. But there's thoughts from some of the models that might tend to lift out a little bit, reducing the shear, combined with warmer water, potentially meaning more of a threat to Hawaii in the future. We haven't really... 2015, Hawaii dodged so many bullets, and 14 and 15, I mean, you kept thinking storms were going to hit, but there's a lot of cold water right near Hawaii, and unless a storm comes from the south and goes straight north, like Iniki did, it's really hard, because what was it? We had, was it Madeline and Lester, and it was like all of a sudden it was like, you know, 2 massive hurricanes are going to plow into Hawaii, and they both just kind of like, Hawaii just ate them. They split, and they fizzled. So, well, hopefully, but again, with climate change, you don't really know. But again, there's uncertainty more when you start getting into the regional scale impacts of the TCs. Yeah.
Bill, you may have said this, Todd Santos, CBS Buffalo. Back to the thermohaline piece of this, how far back does that data set, is it quality enough to correlate into this whole thing? Well,
so obviously, too, you have the hurricane data, which gets really dodgy as you go back in time. If you look at multi-decadal signal, and you can pull North Atlantic multi-decadal variability going back to at least the 1600s with marginal observational data. And then the ice cores and stuff seem to show going back even further. And obviously the time scales, it's not a nice, neat, like, hey, it's every 30 years, it shifts and you can predict it. But there does seem to be this kind of multi-decadal variability on, say, 30, basically it's like 30 high, 30 low-ish, plus or minus 5 to 10 years. But you do see this kind of multi-decadal variability in the Atlantic going back pretty far. And if you look at the hurricane variability, once you get prior to about 1900, the basin-wide data is just useless. But if you look at the landfalls, you can still kind of see some of this multi-decadal variability, but that gets challenging because you're subsetting a data set. And obviously, if all you did is had landfalls since 95, it wouldn't look like that active of a period because we've had more storms recurving. But we know it was active just because we can observe the basin-wide. So it does get dodgier as you go back in time. But you can see multi-decadal variability in various climate modes as well. Yeah.
Right over here. Hi, Phil. Hey. So I know that you're showing skill with the number and the ace, but when do you think we're going to get better at this skill on, as you showed, the hurricane drop because of steering currents and when it's shifting more towards landfall frequency increasing?
Yeah, I mean, I think in general, probably what we're going to get. So the UK Met model showed some skill at predicting the kind of the cluster in the Northeast Caribbean this year in September. But it's hard to know, like, was that like good luck, or was that actually like, have they done it 10, 20 years in a row? And so I think the challenge is that predicting kind of the large-scale ocean, predicting the large-scale ocean is fairly straightforward. There's a lot of just, once you get into like June, July, like if it's the anomalies in the Atlantic are warm in August, they're probably going to be warm in September unless you have crazy hurricanes going across, because your trade winds aren't that strong in the summer. But obviously when you're trying to predict steering flow, that's mid-latitude weather. That, had Harvey made landfall a week earlier, a week later, its outcome would have been very different. So that gets really tricky. But the thing I think we can do probably before predicting the steering better is predicting maybe where the storms are likely to form. Because in general, again, Irma's, as Dr. Gray would say, the exception that proves the rule. In general, stuff forming really far east, the odds of that hitting the U.S. are fairly limited. And if they do hit the U.S., they can be really nasty, but those are typically more limited, whereas storms in like 2005, when storms form in the Caribbean or in the Western Atlantic, they're probably going to hit something. I mean, they can't really, if it's in the Gulf of Mexico, it's got to hit somebody. So I think that's probably where we're going to start going to next in terms of probably before better than with the steering. I know there are some numerical models trying to do it, and maybe if we can get dynamical models in June predicting the steering flow better, that can really help. And they obviously, dynamical models also do predict seasonal numbers. All those techniques aren't all statistical. There's a lot of hybrids and, well, some just pure dynamical model output.
Awesome. Well, Phil, thank you very much. It's been terrific.
Sure.